you guys an example of a numerical example that motivated the way I actually solved this problem. And let me just write this. Y'all, this reads 9 raised to the 9th power. Now, I claim that it divides 21 raised to the 21 power. And if you'll notice the Sierpinski problem, that's exactly what they're saying. Find integers x and y distinct such that x to the y divides y to the y. Well, this one does, and this isn't too difficult to see. If you look at 21 to the 21st, this just means that you get an integer. In other words, 9 to the 9 is a divisor of 21 to the 21st. So you can write it more conventionally as 21 over 9 to the 9th. And you're going, how in the world would you know this? Well, it's pretty easy actually, because this is 3 to the 21st times 7 to the 21st. And right here, folks, 9 is 3 squared, so this would be 3 to the 18th, right? And so this definitely is an integer, right? Because these guys, just laws of exponents, right? You'd end up with 3 cubed times 7 to the 21st power. So it's clear that 9 to the 9th divides 21 to the 21, kind of optically appealing here. Now, I've done most of the work here, and I'm going to show you how to generate. They want a kind of an algorithmic way to give, starting with a positive integer n, to generate such a pair. So, again, I've written most of this down for n is a positive integer, so that here's n's a positive integer. Now we're going to choose k greater than 1, and you'll see why that's important later on. I know it took a lot of discovery for me to get this, okay, but you choose a k greater than 1 such that 2 to the k is greater than the n that you specified. Now it seems kind of complicated, but once you see why it's that way, it's really fairly easy. Now you select a prime that is greater than 2 to the k minus 1 times k. Remember, this was the 2 to the k that was larger than the arbitrary n, okay? So we do these relatively natural assignments. We take x to be 2 to the k. And if you take a look at, well, this problem doesn't really give you much insight on that. But if you assign x equals to 2 to the k and y is equal to 2p, which is greater than k times 2 to the k, okay, you certainly see that x can equal to y, which is a condition in the problem, right? Okay. Now, so we go ahead with these assignments, and you can follow the algebra here. You have y to the y is 2 to the p raised to the 2 to the p. X to the x is 2 to the k raised to the 2 to the k. Now, this part right here is kind of a nice breakout on the exponents. This is just a standard property of exponents where you can split the two apart like this, okay? And then at this stage, since we have the same base, we can subtract. We can subtract this exponent right here from this exponent. And you see, it was important that we chose p to be greater than 2 to the k minus 1. And you can see that right here, because that would mean that 2 to the p is greater than, see right here, so that would make this part an integer. 2 to the p is greater than k times 2 to the k. And so this part right here, let me just circle it. And you'd never do this unless you played around with some numbers. This is just one of the examples I showed you. But this is an integer greater than 0, right? And that's why it was important that k was greater than 1 also, okay? In other words, for this to be true also, okay? Now, so here's just a concrete example that's different. I just arbitrarily picked 15 as my natural number n, right? So this is my n. N is 15. And so 2 to the 4th is greater than n, 2 to the 4th being 16, right? And then I'm just following what this says right up here. P is greater than, we had to choose a p that would be greater than 2 cubed times 4. Well, see, this is 32, right? 2q times 4 is 32. That's 8 times 4 is 32. So I just arbitrarily picked p equals 37. Okay? You could have picked 41 or any other prime bigger than this. Okay? There's nothing unique about any of this. In fact, 1n generates a lot of these conditions. Just, it's not just a one-to-one sort of thing. And so you can see that 37 was the prime I chose. 2 times 37 is 74. And it's cool. It's cool. This is a kind of a nice Python coding thing. You could use this to generate as many of these as you want. And these are called perfect powers as far as I know. Okay, so we have this, and you can follow this along. You get 74 to the 74th is divisible by 16 to the 16. Again, this is very believable, since this would be 2 to the 74th times 37 to the 74th, right? And then, holy moly, what do we have right here? Well, this is 2 to the 4th. 16 is 2 to the 4th, so this would be 2 to the 64th, right? So again, as before, and I can go ahead, I have the room to write this out. This is certainly an integer, isn't it? It's 2 to the 10th times 37. And again, y'all, these numbers are unpronounceably large, right? It's nice to work with exponents. So I hope that made sense, folks. It's not a fair problem to give you, because this is one that I discovered, and Sierpinski had some others, like another one is 4 to the 4th. This is probably the smallest one, 4 to the 4th. The smallest one, albeit huge, 10 to the 10th, right? And you can just see that one in your head almost. 4 to the 4th divides 10 to the 10th, and there's others. And this is kind of where I got the idea about choosing the 2, okay? And also that was Sierpinski's solution also. And this did come from a Sierpinski, I don't know if the guy's still alive, famous Polish mathematician, number theorist, and had a lot of other interest. Okay, so anyway, hopefully that gets the job done. We took an n and we generated an n. From that n, we generated a fraction of this form that is an integer. Okay, all right, that does it. Thanks for viewing.